And here our next important topic is degrees of freedom of a mechanism. So this is also called as the mobility of the mechanism. In the name itself we have mobility means possible motion. So for example, if you consider any mechanism or any planar or a spatial mechanism, for a given input motion, how many output motions can be possible? How many output motions can be possible for a given input? This input may be one or two motions. It depends on our requirement or the mechanism or type of the mechanism. So if you know output possible motions, then we can choose that particular mechanism for the appropriate application. So how to find out this? And otherwise, if I consider in the other way, like I want to choose a particular mechanism for the particular application. So how to choose that mechanism? So that is either through the trial and error method. So we construct a mechanism and we'll see whether that is satisfying our required application or not. But that is very cumbersome, and every time we cannot go for that. It takes a lot of time also. But instead, if you have a ready-made formula to calculate any degree of freedom of any mechanism, then it's easy to choose that particular mechanism for the required application. Or same point I would like to explain with an example. For example, we have this slider crank mechanism. So this is the slider crank mechanism, and this can be this will be used in our internal combustion engine. And we know that in an internal combustion engine, this motion, translation motion, should be given to the crank as a rotational movement. So that means if you here, due to fuel burning, this piston will be moved in this direction, so that this will be this output. For example, we are considering this as a input motion, and this rotation is the output motion. And we need to know whether this particular mechanism is only of 1 degree of freedom. So that we know it's only 1 degree of freedom because we have already seen this one. But how to know that one before using in the mission or in the engine? So we need to apply these degrees of freedom of formula for this one, and if it is satisfying that output motion is only having only 1 degree of freedom, then only we go for this type of mechanism. And that is about degrees of freedom. But what is the nature of DOF? But in the same example, we know that for a given input motion, this output is only one motion, that is a rotational motion at the crankshaft. But I said only rotational motion only by experience. But if you start newly this mechanism, if you are a new fellow and you don't know about anything about this mechanism, and you want to confirm whether whether the output motion is a translational or rotational. So this nature of the degree of freedom gives the or it distinguishes the degree of freedom is either translational or rotational. So here in this present chapter, most of the mechanisms that we consider are in the plane or planar. So here in the planar, we can easily identify the nature of degree of freedom. But if we consider the same mechanisms in space, then it's very difficult to find out the nature of degree of freedom by using this simple formula that we are going to derive in this session. So in that case, generally people go for screw theory analysis, and they formulate some inverse and direct kinematics, and from that one they segregate some matrices and then find out the eigenvalues, and based on the eigenvalues they will get to know about the degrees of freedom, number of degrees of freedom, and as well as nature of the degrees of freedom. Nature means whether the degree of freedom is a translational motion or a rotational motion. So here, but we don't go in the detail here in this chapter, because our main focus here only on the planar mechanisms. So that's why we need to know degrees of freedom for any mechanism, so that we can use that particular mechanism in a appropriate application. So uh, let's find out a formula for the degrees of freedom. And see, in this particular example, we need to find out degrees of freedom of this mechanism, but this mechanism again consists of different links. This is a slider, this is the simple simple rod, or we can call it as a link, and this is one more link, and this ground also one more link. Here we have a pin joint, here also pin joint. Pin joint means hinge joint. Hinge joint allows only rotational movement between two links, and here also one hinge joint, and this link is again connected to the slider with a hinge joint. So here, if you can find out these degrees of freedom of the individual links, and if you can formulate the relation between these different degrees of freedom of these different links when these are connected by a hinge joints or some other joints, then that will automatically gives the degrees of freedom of the entire mechanism. So what I am trying to say is, instead of directly considering this whole mechanism, I would like to start degrees of freedom of the simple link initially in this space, and then we will move on to the planar or plane. Then finally we try to find out the ultimate formula for the degrees of freedom, and then we would like to apply the same formula for the different mechanisms. And before deriving that particular equation, here I would like to first write the degree of freedom. That's a group. According to Gruebler's criteria, degrees of freedom is given as 3 into n minus 1 minus 2 into p1 minus p2. This is in a plane. This is for planar mechanisms. And when I say mechanisms, that means one of the links is fixed one. Here n refers to the n equal to number of links in a mechanism. N is the number of links in a mechanism, and what is the p1 and what is the p2. So we will define that one, and don't remember, or no need to buy. We would derive this particular equation by considering set of examples. First, I will consider a body in space or three-dimensional coordinates system. This is a body, and at the center of the body, this is the y-axis, and this is x-axis, and this is z-axis. We always follow this convention. This is a right hand thumb rule. So for example, my right hand is going from x to y axis. So x to y axis, if I going from x to y axis, this thumb indicates the z axis. But if you consider x here and y here, then automatically z go in the downward direction. So we always stick to this right hand thumb rule. And if I consider a body like this, and without constraint or without attaching any this body to anything, this body can translate in the in this direction along the y axis, and it also can translate along the x axis freely without any hindrance or no restriction, and it also can translate along the z axis, and the same body can rotate along the y axis, about the y axis, and the same body can rotate about the x axis and also about z axis. So can we say that the body has a 3 translation plus 3 rotations? So that means altogether it has a 6 movements. So can we say that this body has a 6 degrees of freedom? Why? Because degrees of freedom is nothing but possible movement of the body, whether it's a translation or a rotational. Here 3 translation and 3 rotational. So altogether it possesses 6 degrees of freedom. This is in the space. That means if you consider 3 degrees or 3 coordinate system, but I would like to consider the same body in a plane. So what happens if I consider it in a plane? So this is the plane x and y. So this is the body. So this is some rigid body, and this can translate along the x-axis even in this direction or in this direction without any constraint, and this can translate along the y-axis. So it has two translation motion, because here z-axis is missing, it cannot translate or go out of the plane. And if I put my finger at this point O, and if I rotate this body like this, it can also rotate along the axis that is coming out of the plane. So it got one rotation also. So when you consider the same body in the planar or plane, then planar coordinates are in a plane, then it has only two translation and one rotation. So altogether its degree of freedom is 3. And how many constraints it got imposed on this one compared to the space? So 3 constraints. So one constraint in the translation motion and 2 constraints in the rotation. So there are 3 degrees of freedom lost when you shift your coordinate system from the space to the plane. So, and in most of the mechanism that we are going to deal in this chapter are planar. So we would like to derive these degrees of freedom for the planar mechanisms. So, and before going into the derivation here, I would like to consider some other types of links and the possible degrees of freedom and a constraint between those links. In the first one we have a slab or a plane, and this is a sphere, and these coordinates are like this, and this is the origin at the center of the sphere. The sphere can travel along the x-axis and also along the y-axis, but it cannot travel z-axis. It can only go upward direction, but there is a restriction when it is try to go in the downward direction of the z-axis. So here it has only two translations, one is along the x-axis and another along the y-axis, and it can rotate about x-axis and then y-axis and then z-axis. So for example, if I consider this as the sphere, so it can rotate like this and it can rotate like this, okay, and it can rotate like this, and it can rotate like this also, about this one. So it has 3 rotations. It has 3 rotations. So altogether, how many degrees of freedom does this sphere possess? So that is a 5 degrees of freedom, and there is only one constraint, that is a translational constraint in the direction of z-axis. And if you consider this example again, we have a sphere inside a hollow cylinder. So this we have a sphere inside a hollow cylinder, and we would like to find out how many degrees of freedom that this sphere inscribed in a this sphere can translate only along the x-axis, because this is a hollow one. It can travel here and in this direction, but it cannot travel in the y-axis and the z-axis. So it has only one translation, and this sphere again can rotate about x-axis, y-axis and z-axis, because there is no constraint, or the sphere is not attached to anything. So it is like a globe, so it can rotate in any direction because that rotation is not constrained. So again we have 3 rotations. So total degrees of freedom of the sphere inside the cylinder is 4 degrees of freedom, and there are 2 constraints in a translation motion along the y and z axis. And again here in the third case we have a cylinder placed on a plane. So again the cylinder can move along the x-axis and also along the y-axis. It can go like this or like this, but it cannot go along the z-axis. In the negative z-axis direction it cannot go. So only 2 translations are possible, and rotations. So it can rotate about x. This is the cylinder. If you consider this is the cylinder and this is the x-axis, it can rotate like this, it can rotate like this, and this is x-axis and this is the y-axis, this is the y-axis. So about y-axis, can it rotate? No, it cannot rotate, because this is the y-axis and it has to rotate like this, but we have a plane here, so plane is opposing that one. And this is the z-axis and this is the z-axis, and it can rotate like this about the z-axis. So it has only 2 rotations, 2 translation and 2 rotations. So total degree of freedom is 4. And here we have, in this case, this is the sphere, this is the sphere, and the sphere is locked inside a groove. For example, this is a groove, this is in 2D, but you imagine in a 3D. This is a groove, and inside we have inside the groove we have a sphere like this inside the groove, and the opening of the groove is such a way that it should be less than the diameter of the sphere. If the opening is more than diameter of the sphere, then sphere will come out. So that means this groove is holding this one, but the sphere is not attached, but it cannot come out of this one. That means it cannot translate in any of these axes. So it cannot translate in x-axis, y-axis or z-axis, but it can rotate about the x-axis, y-axis, z-axis, because this sphere is not attached or not fixed to this groove. So it can rotate. It can rotate about x, y and z-axis. So here 0 translation plus 3 rotations. And if we have, in any mechanism, if we have this type of arrangement, then that can be called as a ball and socket joint. This sphere is a ball and this groove is called as a socket. So ball and socket joint. In our human body we have so many pairs of this ball and socket joint. For example, our shoulder is best example. This is the shoulder one, and this is the hand. This is the hand and this is the ball. It looks like a spear, right? And this is the groove or socket. That is our main body. This is our main body, and at the end of this one we have groove like structure, and hand is a spear like structure. So here this translation is not possible, but only 3 rotations. How these 3 rotations? For example, one axis is like this, and one axis is along this one, and one axis is coming out of the plane. So for example, if I consider one axis along the hand of this one, so what is the rotation of this hand along about this axis? That should be like this, like this. We can make rotation like this, right, about this axis. And if I consider axis like this, one more axis like this, so what is the rotation of this hand about this axis? That is like this. This is the axis, and I am making rotation like this. And another axis, third axis, is along this one. For example, if I consider third axis along my body like this, then I need to rotate my hand in this direction. So we have 3 rotations here. So that's how our shoulder joint works. In this example, we have a cylinder inside a hollow cylinder. So this cylinder can move in this direction along the x-axis, that is, but it cannot translate in either in y-axis or z-axis. Here we have only one translation motion, and it can rotate about the x-axis also, because for example this is the x-axis and I can rotate like this one. So here we have one translation and one rotation when you have a cylinder inside a hollow cylinder. And in this case, this is the same one, but here we kept one collar here. So why we kept this collar? So that it will, if you keep this collar, it will prevent this translation along the x-axis. So here translation is arrested and we have only one rotation about the x-axis. So here only one translation and one rotation and 0 translations. And in this case, this is a prismatic bar, and this can translate only along the y-axis, and it cannot rotate about the y-axis because this is not a circle, so it cannot rotate this one. So here we have 0 rotation and 1 translation, the x-axis and y-axis. And already I have considered a rigid body like this, and this rigid body in a plane has 2 translation and 1 rotation. And if I consider another rigid body like this, so this is a body 1 and this is a body 2, and these two bodies are hinged, are pinned at this position O. So we will see how these combined degrees of freedom are affected. So individually body 2 has 3 degrees of freedom and body 1 has 3 degrees of freedom. But now after hinging, if the body 1 is moving along the x-axis, body 2 also has to move along the 2-axis, and if it is moving along the y-axis, body 1 is moving along the y-axis, then body 2 also compelled to move along the y-axis. So translation motion of the body 2 is no longer independent, but it's dependent on the body 1, and body 1 can rotate about this point O, and body 2 also can rotate about the point O. So body 1 has here 1 rotation plus 2 translation, but whereas body 2, it has only 1 rotation about the O, but its translation motions are no longer independent, but they are dependent on the body 1. So it has only 1 rotation, and these 2 translations are constrained. So can we write the degree of freedom of the combined system that equal to, for body 1 we have 3 degrees of freedom and there are no constraints, plus body 2, actually we need to have 3 degrees of freedom if it is a independent, not hinged up to the body 1, but because of hinge 2 constraints came. So this is a body 1 degrees of freedom, body 2 degrees of freedom. So for example, this can be written as 2 into 3, where 2 is the number of links n. So here in this case we have 2 bodies, that's why here n equal to 2 and 2. So this can be written as 3 into n, where 3 is the degrees of freedom of a link in a plane and n is the number of links, minus 2, where 2 is the number of constraints that is due to this hinge point. So this is the formula that we have derived at. And now we will see what happens if I make this body 1 as a ground. That means if I fix the body 1 to the ground like this. So this is the body 1 and this is the body 2. This is the body 2 and this is the point O, and body 1 is fixed to the ground now. This is the body 1. So body 1 lost is it's 3 degrees of freedom, and body 2 has only 1 degrees of freedom, that is a rotation about the point O. So now degrees of freedom of the system can be written as here for the body 1 we can return, actually it should have 3 degrees of freedom, but it is fixed to the ground, or it made as a ground, so it lost 3 degrees of freedom, and we impose 3 constraints, 2 on translation, 1 on rotation. This is for the body 1, and for the body 2, actually in a plane it has to have 3 degrees of freedom, but because of hinge joint we lost 2 degrees of freedom. That means we impose 2 constraints, so we can written like this. So if I write this one like 2 into 3 degrees of freedom for 2 links, we have, this is the number of links 2, for 2 links 3 degrees of freedom, but this one and this one, this is the constraint for 1 degree, because this is a constraint for the body 1 because it is a fixed one, and this is the constraint for the body 2. So if I take 3 as a common, 2 minus 1 minus 2, where 2 can be written as a number n, 3 into n minus 1 minus 2. So the same equation, I mean whatever we derived in the previous chapter, previous example, here also we got the same equation but with a minus 1. Why? Because here n is decreased by minus 1. That's because one link is fixed, and if we consider this as example 1, and in example 2, here instead of 2 bodies, now I will consider 3 bodies. So this is the ground one, and to the ground we have a body 1 is hinged. This is the body 1 and this is body 2, and to this body I hinged another body 3. So this body 1 has a 0 degrees of freedom because it's a fixed, and body 2 is fixed to this one, so it has only rotation, it lost its 2 translations, and body 3 is hinged to body 2 and it lost 2 translation, and it can rotate only about this point O1, and this is the O. So what is the degrees of freedom of the combined system? That can be written as, first we will write what could be the degrees of freedom of the body 1. For the body 1, actually it should have 3 degrees of freedom, it is not fixed, but since it is a fixed, it lost all its 3 degrees of freedom, so we impose 3 constraint here. This is for the body 1, that's a fixed one, plus for the body 2, 3 degrees of freedom in a plane, but how many constraints? 2 constraints, so 2 translational constraints, and for the, this is for the body 2, and for the body 3, 3 minus again 2, so this is a body 3. So this is the 3 degrees of freedom for body 1, 3 degrees of freedom for the body 2, 3 degrees of freedom for the body 3. So we have 3 bodies, so that's why 3 into 3. So I can write 3 into n, where n is the number of links, minus 3 minus 2 into 2. So 3 into n minus 1 minus 2 into, here I would like to write one more, this instead of 2 I would like to write here as a P1. So let's define what is a P1. Here P1 is the number of pairs with DOF 1. So number of pairs having the degree of freedom 1. For example, in this case, if I consider body 1 and body 2, how many pairs? Only 1 pair. 1 and body 1 and body 2, that constitute only 1 pair. So this 1 pair has only 1 degree of freedom between these two. So not total degree of freedom between these two, because about this point O it can rotate. Point this can rotate, and about point 1 about point O the body only can rotate. So it has only 1 degrees of freedom because of this hinge point. And if I consider this example, between body 1 and 2 we have 1 pair, and that pair is having only 1 degrees of freedom. because here hinge is used to connect the body 1 and 2. So that is a one pair, and we having the degree of freedom 1, and between the body 2 and 3 once again it's connected by hinge point. So we have a one more pair having the degree of freedom 1. So how many? 1 plus 1. So here 2. So this is the P1, and here also we can write P1. But in this case, what is the value of P1? That is the only 1, because we have only one pair of links that is with the degree of freedom 1. But here in this case P1 equal to 2. Here in this case P1 equal to 2. Why? Because here we have two pairs having degree of freedom 1. So in a general sense, can we define dy of equal to 3 into n minus 1 minus 2p1. So here n equal to number of links, and this degree of freedom formula for the mechanism, where in a mechanism one link is fixed, and this p1 is a number of pairs having degrees of freedom 1. So we defined up to this point. Oh, and our next example is this one. Here we have a hollow cylinder. This is the hollow cylinder. This is the body 1, and this is body 2, and this is also cylinder. The cylinder is moving inside a hollow cylinder. This hollow cylinder is a fixed one. So we have already seen when and this is a side view. If you see this one, this is the fixed one. This is the fixed cylinder, and inside the fixed cylinder this blue one is the solid cylinder, and it can rotate like this. It can translate in this direction, and it can also rotate like this. It can rotate like this. So it has 2 degrees of freedom. So degrees of freedom between the body 1 and 2 is 2 degrees of freedom. I mean it has one translation and rotation. So we would like to write degrees of freedom of the combined system. For the body 1, actually if you consider the body 1 in a plane, it should have 3 degrees of freedom, but since it is a fixed, 3 constraints are imposed. This is for body 2, body 1, and for the body 2 it should have how many degrees of freedom? It should have 3 degrees of freedom in a plane, but in a plane 3 degrees of freedom, but here only 1 degree is constrained, that is along this direction, but it is rotating and translating, but in this direction translation is constrained. So only one constraint. This is for the body 2. So this is link 1 3 degrees of freedom, link 2 3 degrees of freedom. So can I write 3 into 2 or 3 into n minus 1? Why? Because here n is number of links, that is the 2 minus 1. So here n is the number of links. Here if I substitute n equal to 2, again we get the same number. So what is the value of this one? 2 degrees of freedom. If I put n equal to 2, again we get 2 degrees of freedom. And here instead of 2, in the next example, here I would like to consider 3 bodies. So 3 bodies having like this. For example, this is the body 1, and this entire structure, instead of fixing everything, I removed this fixed one, and I just attached one hinge here like this. I attached one hinge here, and this is the again solid cylinder that is moving inside the hollow cylinder. This is the body 2, that is a hollow cylinder, and this is the body 1, that's a fixed ground, and this is the body 3. So here body 2 is only rotating with respect to body 1. and body 3 is translating in the body 2 and as well as rotating about this axis. Actually, if you draw an axis here like this, it is rotating about this axis. So body 3 is rotating, so that means it has 2 degrees of freedom with respect to body 2. Body 3 has 2 degrees of freedom with respect to body 2, and body 2 has only 1 degree of freedom with respect to body 1. So here I can write degrees of freedom of the whole system. DOF equal to, for the body 1 it should be 3, but it lost all 3 because it's a fixed one, and for the body 2 it should be having 3 but 2 constraints, because only one rotation is possible at the point O. So 2 constraints, and for the body 3 but only one constraint, because it has a 2 degrees of freedom. So can I write like this? Only one constraint for the body 3. So this can be written like this: 3 into n, again minus 1 minus 2 minus 1. So here this n is number of links. Here in this case it's a 3, and this 2, and you have 1. So this can be written as 3 into n minus 1 minus 2 into p1 minus 1 into p2. So where p1 we have already seen. What is the p1? And if I compare this equation, with this equation, in the above equation this 2 is missing, but here in this equation we got 2. That's because we got some hinge joint, and because of the hinge joint we got one extra pair of link that is having degrees of freedom 1. So that's why we got 2, and whenever we use a pair that is having degrees of freedom 2, we are getting only one constraint. So here in this case, that's why this hinge joint is missing, and we have a pair of the links that is having degrees of freedom 2. So that's why only one constraint. So what I am trying to summarize here is, this can be written as p1 into p2, where p1 is the number of pairs of links having degrees of freedom 1, and where p2 is the number of pairs of links having degrees of freedom 2. Here in this case p2 is how much? What is the p2? This is the only 1, because here what p2 pair is only 2 comma 3. These two links are having degrees of freedom 2, and what is the p1 in this case? P1 equal to only 1 and 2. That is the links are pair 1 and 2, body 1 and 2 as a degrees of freedom 1 between them. So finally we can insert one more term here, 1 into p2, where p2 is the number of pairs having degrees of freedom 2. So this is the final formula that we have already seen at the starting of this chapter. So we have derived this formula with a set of examples, and here before further moving, I would like to explain one more concept. Like in the previous example, we have considered this example, like one body is this is a body 1, and this is the body 2, and this is the body 3. So instead of having hinge here, if I write these 3 bodies like this, this is the body 2 and this is body 3. This is 2 and 3. So is there any difference of calculating degrees of freedom in this case? No, let me see that. For example, body 1 degrees of freedom is, in this case, what is the degree of freedom of the system? That is 3 minus 3 0, 3 for the body 2, 3 minus 2 1, and for the body 3, 3 minus 2 again 1. So 1 plus 1, 2 degree of freedom. And for this one, for the body 1, what is the degree of freedom? That is a 0. For the body 2, what is the degree of freedom? 3 minus 2, because its a translation is constrained, so that is 1. And for the body 3, what is the degree of freedom? That's again 3 minus 2, so 1. So in the both cases, degrees of freedom are 2. And here we have used 2 hinge joints, but here instead of using 2 hinge joints, we used only 1 hinge joint. But if we go from the formula, what is the degree of freedom? That is the 3 into n minus 1. Here n is a 3. 3 into n minus n. 3 minus 1 minus 2 into p1. So what is the p1? So p1 is the number of pairs having 1 degree of freedom. So here, what is the pairs? So can we write pairs like this? So one may attempt to write pairs like this: 1 2, 1 3, and then 2 3. So how many pairs we got here? 3. So that means p equal to 3. So if you substitute this one, how much this one? 6 minus 6. So then we get a degree of freedom as a 0. So that means number of pairs that we calculated here is wrong. So we should remember this one. So don't tempt or don't confuse to calculate number of pairs here as a 3. Why? Because here we are using only one hinge joint at the point O. So with one hinge joint, we are connecting all three these bodies. So that means or let me say, for example, at the point 1 we have a projection like this, and this link 2 and link 3 already connected to this 2 and 3. These are already connected and formed a pair with a hinge joint like this. Okay, so this is already a pair, and how many pairs? This is the one pair, p1 equal to one pair here. And if I put this hinge joint in the body 1, this is the body 1, and I just simply putting this hinge in this needle like this one. So this already one pair is together considered as a one link, because it's already formed a pair, and that is kept in this needle. Again, with 2 and 3 together considered as a one link, and 2 and 3 and 1 formed another pair. So here how many pairs? P1 is 2 pairs. 2 pairs having degrees of freedom 1. So whenever we have a situation like this where more than two links are joined with a revolute joint, then P1 or number of pairs having degrees of freedom should be taken as for example, these are J links. How many links these are? J links at this particular joint. So P1 at this point equal to J minus 1, simply J minus 1. We need to take, and we should remember this formula. This is very, very important. And P1 at this point is J1, where J is the number of links at this particular joint O. Okay, this is not equal to number of n. In this case, it became J equal to n. But if you have a further something like this, I have link like 4. So here n is 4, but J is again 3 at this point O. So how to calculate number of pairs having degrees of freedom at point O is J minus 1. So 3 minus 1. So that is a 2 here, and one more point here. So that is a 1. 2 plus 1, 3. In this particular case, if n is a 4. So this is how we need to calculate, and we should remember this one. Degrees of freedom equal to 3 into n minus 1 minus 2 p1 minus 1 into p2. here minus 1 because one of the links is fixed, and what if link is not fixed. So if any one of the links are not fixed, then this formula is simply this. So this 1 minus 1 will be removed, and this is the formula, and these two formulas are for the planar mechanisms.